Hi, it's time for another math easy solution. Turn to discuss further into differential equations and now look further into Newton's law of cooling that I introduced in my last video, so make sure to watch that. And now I'm going to go over example 1 of this example series on this Newton's law of cooling. Basically going to solve this example, which states a bottle of soda pop at room temperature, that's 72 degrees Fahrenheit. Yeah, which is about, I think this is about 22 degrees Celsius, so roughly that. Yeah, just if you're not familiar with Fahrenheit. So it's at room temperature and it's placed, in a refrigerator where the temperature is 44 degrees Fahrenheit. And this 44, again, this is about roughly 6 to 7, I'll just round it up to, this is roughly about 7%, 7, not percent, degrees Celsius. Just to get an idea if you're not familiar with it, again, because I'm not too familiar with Fahrenheit, I use Celsius here in Canada. So, yeah, so the soda pop is, it's room temperature, then placed into the fridge, and then after half an hour, the soda pop has cooled to 61 degrees Fahrenheit, and where this 61 is roughly equal to, I think this is about 16 degrees Celsius. And now the part A of this example states, what is the temperature of the soda pop after another half hour? And then part B says, how long does it take for the soda pop to cool to 50 degrees Fahrenheit? And where this 50 degrees Fahrenheit, again, this is about 10 degrees Celsius. So let's just go ahead and solve it. So the first thing we have to do is, again, is basically define our terms. So before I get to part A, we'll try to get a formula for this this cooling of the soda pop. So let temperature, let T of T be the temperature. So this is the temperature, and we're going to use this in Fahrenheit. And then my calculus book uses time in minutes, the temperature, and since we're only going to be dealing with 2 times, that's half an hour and half an hour later, so 30 minutes and then 60 minutes, like that. And yeah, so be the temperature at time t, where this is in minutes. So time is in minutes and the temperature is obviously in Fahrenheit, because that's what this question is involving. So first thing we have to do now is, recall from my earlier video that, what's the title of this video? That's Newton's law of cooling. And Newton's law of cooling states that the rate of cooling, dt over dt, is equal to, or is proportional to, the difference in temperature and its surrounding temperature. So K, that's a proportionality constant, T minus T of S, where this T of S is the surrounding temperature. Yeah, that's the surrounding temperature, and the T, again, just for clarification, so it would be the temperature of the soda pop. So this is of the soda pop. And then right when you place it inside the fridge, the surrounding temperature is this T of S. And again, I went over this in my last video, so make sure to check that out. So we have this part here where, where T of S is the surrounding temperature. Yes, surrounding temperature, and in our case, this is the fridge. So this equals 2, and that's because we're putting inside the fridge. So we want to model the soda pop temperature. So the surrounding one is 44, and we'll just assume it's always 44. So it's equal to 44 degrees Fahrenheit, or roughly 7 degrees Celsius. Yeah, so thus what we have now is our differential equation becomes dt over this dt equals to k, and then t minus 44. Let's erase this line. And now before we get further, and again, as I went over my last video, you could simplify this further by writing, writing this let. So we're basically going to change a variable. So let y of t equals to the difference in temperature, so t minus 44. And the reason we're doing this is because, the derivative of this y prime of t, this just equals to, this is a constant, that goes to 0, equals to the derivative of the temperature, or the rate change. In other words, we have dy over dt is equal to d capital T over dt. So now we could replace this differential equation right here. Yeah, we can replace this now with this y. So basically recall, because this is the formula that I went over before, and we already know the solution to it. So this dt over dt is just dy over dt, and then this equals to k, and now this t minus 44, that is just, that is our y. That's this part here equals to y. So that equals to ky, like that. So dy over dt equals to ky, because we let it equal to this. And we also know that the solution to this is, yeah, so again, the solution to this that we went over many times in my earlier videos is simply y of t equals to the initial value of y of 0, if we're given it, e to the power of kt. So that is the formula we've went over before. So make sure to watch my earlier videos on exponential growth and decay to see the proof for that. So once we solve for this difference, then we can easily solve for the t function. So we know, because we have to solve for this y of 0 and this k. Well, we already know what y of 0 is. The soda pop is at room temperature 72. So if it's at room temperature, we'll assume that that's also the temperature. T of 0 is initial temperature of the soda pop. So assume that the room temperature is the same as it, because it's just assumed it's been there for a long time, so it should be the same temperature. So that 72 is the T of 0, and we also know after half an hour the soda pop is cooled to 61. In other words, this is, I'll put an arrow like that, T of 30, because we're doing with minutes, half an hour is like that, is 61 degrees Fahrenheit. Erase this, write it neater. So yeah, so 61 degrees Fahrenheit. So scrolling up here, so we know that not y, because it's a different variable. So T of 0 is equal to 72 degrees Fahrenheit. And we also know that T of 30 minutes, after 30 minutes, is equal to 61 degrees Fahrenheit. So if we know T of 0 is that, we have to solve for y of 0. So y of 0 is simply equal to T of 0 minus 44. That is this part right here. Just plug that in. So that's T. So this one's equal to 72 minus 44, which equals to, well, 70 minus 40 is 30. So then we have this 32 minus 4, that's just 28. So the difference is 28, and now we have to get y of 30. Yes, so now that we know it's 28, before I get to the y of 30, so this is 28. So what we have is y of t is equal to 28 e to the kt. And now we could plug in this to solve it. So what we also have is y of 30. This equals to, well, this is going to be T of 30 minus 44, which equals to, this is 61 minus 44. 60 minus 40, or 61 minus 40 is 21. 21 minus 4 is 17. That's just a quick way of thinking about it. So we have that. So we have this new formula, and we have this y of 30. Let's just plug this in now. So y of 30 is equal to 17, which equals to, equals to 28. And now we have e to the k times t, which is 30. So now what we'll do is just rearrange this to solve for k. So we get a, this is divide both sides by 28. So we have 17 over 28 equals to e, put the 30 in front, 30k. And now again, like always, we just ln both sides so that we get rid of this ln e based on the natural log properties, and you can see those in earlier videos as well in the video link below. So this becomes, this part here is just 30k. So now we could just rearrange or divide both sides by 30 to get the k. So we have k equals to 1 over 30 times ln of 17 over 28. So that is our k value. And here now, if you plug this into the calculator, here's a Google calculator, we get about negative, so yeah, here we have 1 over 30 times ln 17 over 28. So we plug that in, we get negative 0.01663, etc. We'll just stop at this point there. So this is roughly equal to negative 0.01663. So that is what our k constant is. And again, recall that the units for the k, this is just, I'll put this in, this is units of 1 over minute or 1 over time. So we'll just put it like that. And you could see that over here, the t, so we have t times k. Usually when you have e to the whatever, it should be unitless. And also that the k is a relative growth rate. Now 1 over before, the units are 1 over the time. So time is in minutes, k has to be 1 over minutes so that they cancel out. So that's what we get there. And now we could put this all together to solve for the t. So we have y of t is equal to 28 ekt, which equals to, no, before I plug it in just to save time, leave it like that, and then this equals to, by definition, or what we let it equal to, so it equals to t minus 44. So rearrange this, we get t of t equals to, we just move the 44 on this side, 44 plus 28 e to the, and let's plug this in, 0.01663 times t. So that here and this has to be unitless again, because when you have e to the whatever here, it needs to be unitless so that we have this units all match up. So temperatures in Fahrenheit, this is Fahrenheit 44 degrees, surrounding temperature 28 degrees is that initial difference, and then multiplied by, this has to be unitless so that these both add up to Fahrenheit. So that's why, again, that this has to be over minute so that the time and the k units cancel. So we have, this is our formula now. Let's see, do a better square. So that is our formula. And now from here we could solve part A and B. And so part A says, what is temperature of the soda pop after another half hour? In other words, we want t of 30 plus 30, 60. So let's just start solving that part. So part A is t of 60 is equal to, well, let's just plug that in to our formula for temperature. E, this is negative 0.01663, and then this is 60. Yeah, and here I've plugged this into the Google calculator as well. So 44 plus 28 times e to the negative 0.01663 times 60, and we get 54.3, etc. So what we'll do is simply just round up to the 0.3. So this is about 54.3 degrees Fahrenheit. And again, for reference, this is roughly equal to 12 degrees Celsius, just to get an idea of it. So after another half hour, or after a total of 60 minutes or 1 hour in the fridge, the temperature dropped from room temperature of, of 72 degrees Fahrenheit, or about 22 degrees Celsius, all the way down to 54.3 degrees Fahrenheit, or about 12 degrees Celsius. So now let's look at, well, part B. So part B, let's see what that states. Part B says, how long does it take for the soda pop to cool to 50 degrees Fahrenheit, or about, this is 10 degrees Celsius. So what we need to find is, well, we want time, we want t such that the final time temperature is equal to 10 degrees Fahrenheit. So in other words, actually, it's not 10 degrees, 50 degrees. Let me go back. Yeah, 10 degrees Celsius, or 50 degrees Fahrenheit. I got those mixed up. So we want that. So what we could do is, well, just plug that in. So t of t is equal to 50, and this equals to, well, just plug that into the formula. So 44 plus 28, and then we have e to the negative 0.01663, and this is going to be this is t, not 60, so that's just t. So now what we have to do is move this over to this side, divide by 28. So we end up having is, just simplify this, 50 minus 44 over 28. So we move this over and then divide both sides by 28. This cancels, so we get now e. I'll move this over because again we're always going to be taking the logarithmic of it, so natural log of it. So e to the negative 0.01663 t, and now take the ln both sides to cancel that e. So what we get is, well, 50 minus 44, that's just 6. So we get ln of 6 over 28. We could simplify or just leave it like that. My calculus book just leaves it. So we'll just leave it, and this goes down, so negative 0.01663 t. And then solve for t, so t is equal to ln 6 over 28, all divided by negative 0.01663, like that. So that's what our t is equal to. Yeah, and here if you plug it into the calculator, here's ln 6 over 28 divided by negative 0.01663, and then this gets about 92.63, etc. We'll just round it up to 92.6 and recall the units for time. This is about 92.6, and then the units are minutes. So in other words, this could also be, you could also write this as well, 60 plus 32.6. It's the same thing as writing down, these are both in minutes. So if we have this is 1 hour, then we'll just round that up to 33 minutes. So what you could say is that this is roughly equal to 1 hour, just for more practical terms, and 33 minutes. Oops, bad E. So in other words, it will cool down to 50 degrees Fahrenheit after about an hour and 33 minutes, just above an hour and a half of time to wait when you put the soda pop in the fridge. And another note that I want to make is, well, what happens when you wait forever? So in other words, note, this is pretty interesting. So note that, well, if you were to wait forever or just an infinite amount of time, the soda pop should match up with the temperature of the fridge. So in other words, note that the limit as t approaches infinity, I'll put this a bit more sidewards. So of t, this one, well, the formula is equal to, this is just equals to limit as t approaches infinity of 44 plus 28, this is e to the now 0.01663 e. So if we plug this inside, we take the limit as you wait, well, infinite amount of times. Same thing as writing, that's just a constant, so it doesn't change by the limit. And then plus 28 is still a constant, we take it out. So this is times by limit as t approaches infinity, and I'm going to put this negative at the bottom so it's easier to comprehend. So make it a positive power by moving it at the bottom. That's just what the negative means. 6.3, and this is a t, not an e. Like that. And now what we have here is, well, when you take the limit over this one, this is approaching, this is e to the power of, of a number here as t goes to infinity, or you have a 1 to an infinity, which is going to 1, e to the infinity is going to infinity. So we have a 1 divided by infinity, which 1 divided by a large number, you're approaching 0. So in other words, this equals to 44 times or plus 28, and that goes to 0, so we have 0. So in other words, this just equals to 44 degrees Fahrenheit, which is our surrounding temperature T of S. So in other words, this is i.e., for example, the fridge temperature, or the refrigerator temperature. And in fact, here I've graphed that out using that Google graphing calculator, just put in the Google search. So we have 44 plus 28 e to the negative 0.01663 times t, and we have that again. So, and then yes, we have 44 there, and then this one y is 44. Just assume it's temperature instead of y. So that is our temperature, and then this is our time temperature. Yeah, you couldn't have a y in the Google. I mean, couldn't put capital T in the Google calculator. So we'll just stick with that. So as you can see here, this is the graph for that function, and then we put the limit. It should go to 44. This line right here is our temperature equals to 44 degrees Fahrenheit. And then as you can see, the formula for temperature keeps going down and down, so the temperature is getting closer and closer to the surrounding temperature, or T of S, of the fridge right here as you go to infinity. And this is getting closer and closer, but technically never reaches. But yeah, it is. When you take a limit to infinity, that's what you get. So it's a limit, and it keeps getting closer and closer to the surrounding temperature. Anyways, that's all for today. Hopefully you learned from this pretty extensive example on something as simple as putting a soda pop in the fridge, but it's some pretty interesting mathematics behind the temperature cooling or temperature change of that based on the surrounding temperature of the fridge. Anyways, that's all for today. Hope you learned, and yeah, it's another interesting thing is you could even put an experiment and put this in the fridge yourself and see if this model works pretty accurately. Anyway, that's all for today. Hope you learned. Like always, you can download these exact notes in the link below, and thanks for watching, and stay tuned for another Math Easy solution.